Yesterday we graphed simple polar equations, right? R equals a constant and theta equals a constant. And that was learning target 2. Learning target 4, we're going to graph actual polar equations, okay? And so we'll be graphing those all via a table of values. So that's why I'm telling you to have your graphing calculator, because we can fudge that a little bit and take some time out of doing those problems, all right? Instead of having to do everything by hand, okay? So there are 6 types of curves that we're going to talk about that you can create using a polar equation, all right? So your note sheet, the first page is front and back, and it's just reference. The first part of the homework is going to be to go through and identify, based on the equation, what kind of curve you get. Then I'm going to have you graph 6 of them out of the, I think there's like 12 or so that you have to identify. Then you have to graph 6 of them that I told you to graph in the homework. Okay? On the quiz, just so that no one has major panic attacks now. On the quiz, I will give you a table that I'll show you in a second from your book, and you'll have to be able to identify which type of curve is being created for learning target 4, but you don't have to graph any on the quiz. All right? You'll have to graph the ones from learning target 2, so r equals 5 and theta equals 7, or I guess not 7, but theta equals 75 or something. Okay? But you won't have to graph any of the ones we're doing today. All right? So don't have total meltdowns if you're confused. Also, the homework that I assigned today will be due at the end of class tomorrow. We'll add learning target 5 in tomorrow, but it's not graphing and won't take as long. Okay? So if you have questions when you're looking at it tonight or you're confused, you can still ask me tomorrow. We'll do it into class tomorrow. All right? Okay. So we're going to look at this reference sheet together. So the first type of curve is a circle. All right? So if you have a polar equation and it looks like either one of these, r equals some value times the cosine of theta, or r equals some value times the sine of theta, then you're going to get a circle. Okay? Now, I give you lots of information on this reference sheet because it's helpful to know what it's supposed to look like before you start graphing it so you don't get confused. So I give you some extra information here as well. So A, in this case, is the diameter of your circle, so you should know about how wide it should be. And then if you have a cosine equation, then the circle is going to have the left edge at the pole. If A happened to be negative, then it would have the right edge at the pole. I know it's a bad circle. We all know I can't draw anything. If you have a polar equation with sine that's going to make a circle, then the bottom part will touch the pole. If A was negative, then the top part would touch the pole. Okay? So again, you have an idea about what it's going to look like before you even graph it. Okay? Questions about that? You can have circles. You can have roses. Okay? For a rose, it looks very similar to the equation you had for a circle, except the theta is being multiplied by something. So that means your equation is going to say cosine of 4 theta, or sine of 7 theta, or cosine of 8 theta. All right, so it's going to be some number, some value in front of the theta. If n is even, there are 2 times n number of petals in your rose. Again, it's good to know what it's going to look like before you start. So in this case, I have 4 petals. So whatever the equation said had 2 theta in the equation. 2 would have been n, and we have 2 times 2 number of petals. There's 4 petals. In this graph over here, I have 5 petals. If n is odd, there are just n a number of petals. So this equation, whatever the rest of it was, had to have 5 theta in it. So there are 5 petals. Okay? Again, I'm helping you out so that when you start to graph, you know at least have a little bit of a clue what it's going to look like before you start. Your roses will be centered at the pole. Questions about that? All right. We have lemniscates. They have r squared in them, so they're easy to identify. And they have a 2 theta specifically. They make figure 8s propellers. All right, so there's only kind of like a rose with 2 petals. Okay? You have limasones, or snails. These have a plus or minus sign in them. So you have some number plus and minus sine or cosine. All right? Now, you get lots of different shapes with these. So it's important to look at what a divided by b would be to decide what it's going to look like. If a divided by b, absolute value of that is less than 1, you get this inner loop. If a divided by b, the absolute value is between 1 and 2, you just get like a little dimple. And if a divided by b, the absolute value of that is greater than or equal to 2, then you get what looks kind of like a circle, but it's kind of flat on one edge. All right? So again, this will just help you identify which type it is, and you can say, okay, there's supposed to be an inner loop when I graph this. That should be helpful. If you have an equation with sine, the loops and dimples are at the bottom or top of the curve. So these are all sine equations because the loops and dimples are at the bottom. If you had cosine, the loops and dimples are going to be to the right or the left. So again, you have an idea about what's going to happen before you even start trying to graph something. If you don't know what it's supposed to look like and you start trying to graph it, then you won't even know if you're on the right track or not. All right? So you have some sort of idea so that when you start graphing, you're like, yeah, okay, right. This is looking like it's supposed to. We're supposed to have this petal, and then there's another one. All right, that's okay. If you don't know what it's supposed to look like at all, then you're just going to graph some stuff and then hope for the best. So we want to have a clue a little bit about what's happening. We also have cardioids, and there's a special type of limosome. It's just when the absolute value of a over b equals 1. So in this case, b and a are the same number. So for a limosome, you might have 3 plus 2 sine theta, but for cardioid, you'd have 3 plus 3 sine theta. It has to be the same value. So they have a kind of distinct point in the middle. And then the last one is a spiral of Archimedes. These are really easy to identify because there's no sine or cosine in them. It's just r equals some number times theta. And they always make a spiral. They always start at the pole. The important part here, though, is that theta must be in radians. So the polar planes I keep giving you to graph with have degrees on them. So if you have a spiral of Archimedes, you have to change that in your mind. You'll need to change 30 degrees to pi over 6. Right? You can't type 30 degrees into the equation, put 30 degrees in the equation and get out what you're supposed to. Okay, it has to be in radians. All right, so there's 4 examples we're going to look at. Before we do anything, before we start graphing anything or doing anything, we're just going to look at the equations and identify what type they are. Right? That's what half your homework is. It's just saying this is this type of curve. This table you see on the screen is not in your notes. This is what's going to be on the quiz. So for learning target 4, so you're going to have to identify which is which. It's all the stuff I just told you. It's just not all the extra stuff about which way the loops and dimples go or which way sine and cosine are, because you're not going to have to graph them on the quiz. All right, so this gives you kind of an overview, and I will add in a column for the circle part. All right, so you'll have this on the quiz to use as reference to decide which type is which. All right, if you forget your reference sheet at home or something, this is in the textbook in this section. Okay? All right. So we have 4 examples. Again, we're not going to graph anything yet. We're just going to look at which type of curve it is. Okay? So the first one, we have 1 plus sine theta. So if you go back and start looking at your reference sheet, it has to have a plus sign in it. So it can't be a circle. It can't be a rose. It can't be a lemniscate. It might be a limosone. It might be a cardioid, because those have plus signs. And it can't be a spiral. So it has to be a limosone or cardioid, right? So we need to look at the numbers that are being added. We have a number plus some other number. Now, in this case, there isn't another number in front of sine. technically. So what number would be there? 1, right? You'd have 1 times sine theta. Just like you'd have 1 times x. We don't actually write that there. So, are my a and b different or the same? The same. So if they're the same, then it must be a cardioid. Everyone see how I arrived at that? Okay, let's look at the next one. I have r equals 2 minus 3 sine theta, so it has to have a minus sign in it. So again, going through these, can't be a circle, can't be a rose, those don't have minus signs in them. Can't be a lemniscate, so it has to be a limosone. Can't be a cardioid, because the numbers aren't the same, you have 2 and 3. And it can't be a spiral. So it has to be a limosone. Is it making sense where I'm getting this, making these determinations from? All right, the next one says r equals cosine 2 theta. Cannot be a circle, because there's a 2 theta, not just a theta. Could it be a rose? Yes. Make sure we go through everything else. Could it be a lemniscate? No, because it doesn't have an r squared in the front. Can't be a limosone or a cardioid because there's no plus or minus sign in it. And it can't be a spiral because it has cosine in it, right? So it has to be a rose. And the last one, we have r equals 1.5 times theta. What's the one that doesn't have sine and cosine in it? The spiral of Archimedes. Does everyone feel semi-confident at the very least they could go through and identify which type of a curve it was? And that's what you have to do on the quiz, with the reference in front of you. Okay. Again, we are going to be graphing them, though, today. That's why I told you I have your graphing calculator. There is no, like if I tried to explain the ins and outs of every one of the types of these curves so you could graph them without having to make a table, we would be here for a week. All right? So the easiest way to do this is just graph them using a table. When you're using rectangular coordinates, you make a table. You have an x column and a y column, right? You put a number in for x, and you put that number into the equation, you get a number out for y. We're essentially doing the same thing. So we'll do number 5 first. We're essentially, or that's number A on your note sheet. Doing the same thing, except we put a theta into the equation, and we get r out. Okay? So, for example, I'm not going to do this all by hand, because I'm going to show you a shorter way to do that. But this is in essence what we're going to be doing in a second in the calculator anyway. If I use 0 degrees, okay, I put 0 in for theta. And then I would go through this whole equation to figure out what r was. So I would do sine of 0. Well, I would need to know what sine of 0 is. So make sure we're in degree mode. And we would do sine of 0. You could use the unit circle if you wanted to. Sine of 0 is 0. Then it says 1 plus sine of whatever 0 was. So 1 plus 0 is 1. So my r would be 1. And so over here on my graph, for 0 degrees, I would put a point at 1. Does that make sense? That's what we're doing. Now, I can tell you that all by hand, and I can tell you use the unit circle. The problem is the unit circle has like square root of 2 over 2 and the square root of 3 over 2. So you're going to be estimating anyway, because they're going to get decimals anyway. So I'm going to have you cheat the system a little bit, so you don't have to do this all by hand and take 45 minutes to do every single one of these. All right? I feel like I've showed this to you before, but I don't remember. Maybe you learned it in Mr. Scott's class. If you haven't seen it before, I'm telling you now. So there you go. We aren't going to be able to get r and theta. Okay, we're just going to use y and x. we're going to pretend it's y and x. So if you try to graph it, you're not going to get the actual graph, but at least we can use the table. So we're going to type in our equation. So the first one was 1 plus the sine of theta. We're going to use 1 plus sine of x. Okay? Like if you try to hit the graph button, you are not going to get the correct graph. So do not bank on that happening for you. Then we're going to go to table settings. So second window. And if you go to the independent variable, you want to change the independent variable from auto to ask. So instead of filling in the table for you with like 0 and so on, whatever, you can put whatever you want into for the x and get out what you need for the y. Okay? So you're going to change independent variable from auto to ask. And then again, you can hit graph, but you're not going to get anything important. So just hit second graph and go to your table. So again, if I was making a table by hand, I would probably start at 0 and start typing in all these degrees. Right? We already have the degrees on the polar planes. We may as well use them. So I just did 0 a second ago. I can do 0 again. And it tells you that r would be 1. It says y, but we know we're using r. So let's do the next degree measure, 15 degrees. At 15 degrees, then we should plot our r at 1.258. So we're going to estimate, so 1.2-ish, we're going to say is about right there. Does that make sense about what I'm doing? But we're going to keep going. We're typing 30. I'm going to get 1.5. You type in 45. You get 1.7. We know this is a cardioid, and we know it's sine, so know that there's supposed to be some sort of dimple situation on the bottom or the top, right? If you look at your reference sheet. So that kind of gives you a clue what it's supposed to look like. So we keep going with 60. Get 1.8. And then 75. It's a lot less tedious than having to actually type it all into your calculator every single time. And then 90. And we get 2. If I do 105, I go back to 1.96. So that is obviously some point of symmetry. So I can kind of guess where these points are going to be. If you type in 180, you're going to get back to 1. If you didn't realize that was a point of symmetry, that's okay. You could keep typing in degree measures all the way around. Not a big deal. We're not finished. So now we've got to go to 195. See what happens. This will get smaller. So now we're at 0.7. And then 210. We're at 0.5. So we're getting smaller. This should be making sense because it's supposed to be a cardioid. It's supposed to have some sort of dimple someplace. So we get smaller, 0.2. 0.1. So we're getting smaller and smaller. 0.03. And 270 we get 0, so that should be the pole. And then I guarantee when I go to 285, I'm going to go back and find another point of symmetry. So 0.03 is what we had before. So I know this is going to come back out. So there's my cardioid. Could you all do that? If you have your calculator, you can type everything in and then get the point. I'm going to do 1 or 2 more. Didn't come up in this one, but r could end up being negative, right? And if r ends up being negative, we need to graph it on the opposite ray, so you still have to keep all those things in your mind, okay? Was there any questions about the first example? Any at all? Okay. Now I'm going to erase this. On the next one, we already know it's a lemmasome. we go back to our reference sheet about limasomes. We know they make different shapes. We also can determine if the sine or cosines, we know where the dimples and the loops are going to be, right? So I'm going to go ahead and look at it and figure out kind of where I should expect some things to happen and what I should expect to happen so I know what it's supposed to look like. All right, so with that being said, this example is a sine curve. So since it's sine, I know that the loops and dimples are at the bottom or the top. All right, so I shouldn't expect any loops or dimples or anything to the side. So it's going to happen on the bottom or the top. I also know that A is 2 and B is 3 if we're talking about the absolute value, right? So if I'm looking at 2 over 3, I can fit that into one of these categories from the reference sheet. So is 2 over 3 less than 1, between 1 and 2, are greater than or equal to 2? 2 over 3 is less than 1. So I know there's supposed to be some inner loop for this. All right, not just going to have a dimple like the last one, it's going to have an actual loop inside. All right, so by looking at the reference sheet, I've already determined kind of what's going to happen. So it's going to be at the bottom or top of the function. Okay? All right, we're going to do the same thing we just did, though. We're going to make a table, and we're going to graph those points. So I'm going to delete all these out. You can delete them individually. Just go up to the top and hit delete. I need to go to y equals and change my equation. So 2 minus 3 sine of x. And now I can start typing things in. I'm going to start at 0 and just see what happens. Okay? So 0. I have a point at 2. 15. 1.22. 30.5. 45. Right, so 45 gives me negative 0.12. So at 45, that means I'm not graphing a point at 0.12, but I'm graphing it down here at 225.12. Does that make sense? You did that the first day. It's still coming back to HANA. Do 60. 60, I get negative 0.5-ish. And since it's negative, I have to go down here to 240. Graph negative 0.5. 75 is negative 0.9. So I have to go down to 255, put 0.9. Questions about that? $90, I get negative 1. So at 90, I'm going to go down to 270 to put a point at 1. $105, I get negative 0.9 again. So that means over here at 285, put a point at 0.9. That's a point of symmetry, but if you didn't know, you keep typing things in. 120. You get negative 0.5, so at 300, 0.5. 135, negative 0.1, so 315. So you're doing the opposite ray. At 150, we get 0.5 again, though. So 150, we're fine. We just graph right there. $165, 1.2. 180 is at 2. $195 is at 2.7. 210 is at 3.5. 225 is at 4.12, so that goes actually off our graph. Now we already have a point on that ray, but that's because it's the opposite from earlier, right? You can have multiple points on the same ray here, and that's okay. 240, 4.5. Just going around. 4.8. 270 is going to be at 5. We get 4.8, so we're going to start going back closer. So this was supposed to be a limestone with the loop at the bottom or the top. It looks like it's at the top, right? There we go. And if you don't know what it's supposed to look like, it gets confusing in the middle because where we started at 0, we had like looked like a bunch of random points. Unless you're like, oh yeah, there's supposed to be a loop somewhere. It's gonna happen somehow. Questions about that one? All right, I won't graph the rows. You can graph the rows on your own time if you would like. But we can talk about how many petals it would have, so you'd have a clue when you started graphing it. So if you have a rose, you look at the number in front of the theta, that's n. In this case, n is 2. If n is even, there's 2 times that number of petals. So if this n was 2, then how many petals is this rose going to have? 4. So before you graph that, you should know, okay, there's supposed to be 4 petals. But you do the same thing. As we just did, you would type that into your calculator, and you'd use the table and start graphing points. Does that make sense? All right, on the last one, I do want to do this one. It won't take us long at all. For the spirals, your theta has to be in radians. Has to be in radians. All right, that's kind of a problem since the planes I gave you are in degrees, so I have to change some things. All right, what I would do is I would look at your unit circle really quickly and change all the degrees to radians because they're already on the unit circle for the most part. I know that 0 is 0 and 2 pi. I know 30 is pi over 6, and 45 is pi over 4, and 60 is pi over 3. So I'm not having to actually multiply all these by 180 over pi. Sorry, pi over 180. All right, I'm just, from the unit circle, you could look at that. They're right next to each other. Okay. All right, then when we use the table feature in our calculator, since it has to be in radians, we can go back and type in 1.5 times x. That's fine. Not a problem. But because it has to be in radians, your calculator has to be in radian mode. It actually doesn't have to because we're not using sine or cosine. Right? So if you don't change it, it's not the end of the universe. But just keep in mind radians. All right? So we go to your table again. I'm going to delete all these out. The degree values won't work, because if you start putting the degree values in there, you do 1.5 times 15, you can start getting these huge numbers, right? So it has to be in radians. So we have 0. Well, 1.5 times 0 should be 0. That's why all the spirals should always start at the pole, because you would always multiply by 0 and get 0. All right, if we did pi over 6, we get 0.78. So 0.78, right about there. And then we do pi over 4, and we get 1.17. And then pi over 3 is 1.57. Again, it's just to make a spiral, so they're not going to make a specific closed shape. So we get 2.3. And they start getting large rather quickly since our polar plane only goes out to an r of 4. 2 pi divided by 3 would be 3.14. The next one would be 3 pi, 3 pi over 4. And because I can't type things, so we get 3.5. Right, so all this does is you graph some points. We know this is going to make a spiral. So it's going to keep spiraling around. It's going to start going off of your graph, so you can't do much else. If you look at the answers in the book, they're really nice because they made polar planes that go out to an R of like 12 or something. So then you can actually see a nice spiral. We're going to go to 4, so we do what we can. Questions on how I graph these?
At this time, teachers, please excuse all peer mentors to report to the cafeteria at this time.
All right, so you can do the learning target 4. You can start the learning target 4 homework, and I would go ahead and start it because we are doing 5 in class tomorrow. Learning target 4 homework will be due at the end of class tomorrow, though. So I'll get a start on it so you can ask questions in class tomorrow.